Next example. Next example is a particularly fun one. So it's example number 4. Field with 2 elements. So it is denoted by F2. And what 2 elements a field must have? Okay, so one of them is 0, another is 1. So it will have exactly 2 elements. I will denote them by 0 and 1, and you will later see why. So this will be actually 0, this is actually 1. So, okay, we can easily figure out, if we just have this field with 2 elements, what are the rules of addition and multiplication. So 0 plus 0 is 0, because 0 plus anything is the same number. Sorry, 1. 1 plus 0 is 1. 1 plus 1 is, okay, and here it's slightly non-trivial, it can be 0 or 1, but it is easy to see that if it is 1, you can subtract 1 and you get 1 equal to 0, so it will have actually just 1 element, and this is not allowed, so it equals to 0. And also one can check that 0 times 0 is 0, 0 times 1 is 0, 1 times 0 is 0, 1 times 1 is 1. So for those of you who have seen computer science, it is very easy to recognize what these operations are. So this one is just AND, and this is XOR, if this is false and this is true. So this is an example of a field, and it is very important. So later on in the course we will study vector spaces over a field with 2 elements, and they will just correspond to usual sets, surprisingly. Okay, so this is an example of a field, and one can check all the properties. For instance, 1 inverse is obviously 1, and 0 does not require to have an inverse. So final example for us is finite fields. So this is a little bit more complicated topic. So let me denote, let me start with P, a prime number. And then we will define field Fp. Okay, so you see P equal to 2 will give us this one. So field Fp has P elements. As a set, it just has elements called 0, 1, and so on, P minus 1. That's it. And one should think of that as remainders modulo this prime number. So in this way we define operations. So A plus B is by definition remainder of A plus B modulo P. It means we take A plus B and find one of the elements here, so that when we subtract it, the difference is divisible by P. So A plus B equals to C if and only if A plus B minus C is divisible by P. And it is easy to check that there exists exactly one number from 0 to P minus 1 satisfying this property. And similarly, A times B is the remainder of A times B mod P. Okay, so let's practice a little bit. So what the arithmetic in F7 looks like. So it has 7 elements, 0 up to 6. And we can add them. For instance, 3 plus 5 is, so 3 plus 5 is 8, and when we subtract 1, we get 7, so this equals to 1. And 3 times 5, for instance, is 15, and when we multiply, when we take 15 and take the remainder, when you divide by 7, you get 1. So in particular, 3 inverse equals to 5. It is not obvious at all that this actually is a field. And to prove that, you need to know a little bit of properties of divisibility of numbers, but I'm not going to talk too much about that right now, maybe a little bit later. So why I use these funny brackets here and there? So the idea is that actually there is another way to think about these brackets. So to do that, I need to talk about an important topic later on, which is an equivalence relation. So let me do that now. Let me make a little bit of a side remark about equivalence relations. So this is a very general mathematical notion in set theory, has nothing to do with linear algebra or fields or anything like that, which is very simple and very useful. So let's suppose that X is a set. And then an idea is that, of course, we have a notion of equality. Two elements in a set are equal if they are just equal as elements in a set. But sometimes we want to find a coarser notion of equality. For instance, let's take animals, and then we can call animals equal if they are from the same species or something like that. So what does that actually mean, and how to do it generally in mathematics? So an equivalence relation is a set of pairs E inside X times X such that so actually we will denote, so a little remark here is that A comma B is inside E denoted by A is equivalent to B. So this just means that such a pair is inside the set of pairs defining for us the relation. So the following axioms should be true. Firstly, for every element A in X, A is equivalent to A. So other way around, we say that a pair AA is inside E. This property is called reflexivity. The second one is that for every pair, every two elements A and B in X, if A is equivalent to B, then B is equivalent to A. And finally, for every three elements A, B, and C in X, if A is equivalent to B and B is equivalent to C simultaneously, this implies that A is equivalent to C. So as soon as we have a set of pairs satisfying these three properties, we say that we have an equivalence relation, and we call elements A and B equivalent if pair AB is inside E. So example. So let's start immediately with an important example. So a pair of integers A, B, Z, A is congruent to B mod P if A minus B is divisible by P. So this defines an equivalence relation. So what I mean is that one can use this sign instead of this equality. Why? So claim is that this equivalence is an equivalence relation. So proof is very simple. So of course A minus A is divisible by P because it's 0. And also if A minus B is divisible by P, then of course B minus A is divisible by P. And finally, if A minus B is divisible by P and B minus C is divisible by P, then one can add up two numbers divisible by p and get that a minus c is divisible by p. So this is a great example of an equivalence relation. And there are others. So for instance, one can take trees and call them equivalent if they have the same height. So now every tree is equivalent to all trees of the same height. So when you have an equivalence relation, your set of objects, let me draw it here, is subdivided into many different subsets. So these are all elements equivalent to each other, and these are all elements equivalent to each other, and so on and so forth. And basically what equivalence relation does, it takes your set and cuts it along into a bunch of different subsets, which don't intersect and cover the whole set. So this is a little property which I will say right now. Let's talk about equivalence classes. So let X be a set, and this will be equivalence relation. So define for element A in X, X sub A is a set of all elements T inside X, such that T is equivalent to A. So if you have an element A, this all set of elements equivalent to A is called X sub A. It's called an equivalence class. And a little proposition is that for every two elements A and B, XA intersect XB is empty, or XA equals to XB. 1 and 2 is X is a union of all elements sets XA. So what happened here is I just said that our set is presented as a union of non-intersecting, usually people say pairwise disjoint subsets called equivalence classes. Let's prove that. Proof. So suppose XA intersect XB is not empty, and then there exists C inside XA intersect XB. So let's prove that XA is inside XB. Of course, similarly, we will prove the other inclusion. So for every element little x inside XA, we know that A is equivalent to X. But then we know that C is inside XA and XB, so C is equivalent to A and C is equivalent to B. Using this and applying second and third property 2 times, we see that X is equivalent to A is equivalent to C, and C is equivalent to B. And we get that X is equivalent to B, so X is inside XB. So similarly, XB is inside XA, and this proves that XA equals to XB. And 2 is obvious. Okay, so in this way we prove this important proposition, and then the idea is that basically if you have an equivalence relation, this is the same thing as just to divide your set into a few non-intersecting classes covering the whole set. So let's take P equal to 7, and let's look at congruence modulo 7 equivalence relation. So our set is Z, integer numbers, and we cut it into classes. 1, 2, 3, 4, 5, 6, 7. So these are elements congruent to 0, congruent to 1, congruent to 2, congruent to 3, 4, 5, 6. We denote this class. So this class will be denoted by 0, 1, 2, and so on, 6. And then the idea is that basically this 0 in brackets is not just number 0, it is a subset of Z consisting of all numbers divisible by 7. And similarly for all other elements like that. And of course, all the properties of equivalence relation are obvious here, and clearly the sets don't intersect. Here is another way to think about Fp. So before I just said that it has p elements, 0, 1, and so on, p minus 1. But of course, naturally, one can ask what these elements actually mean. We can just say that these are these elements with these names, but more clearly, more conceptually, we want to say that these are something. So here is how we do it. So we start with a set Z is a set integers, and congruence mod p is an equivalence relation. And then Fp is a set of classes of equivalence. So basically element 0, for instance, which we defined before, so element A, which we defined before, is just a class of elements equivalent to A, which are of course just A plus P, A plus 2P, A minus P, and so on and so forth. Okay, so why is a set actually a field? So definition: A plus B, it is just a class of a sum, A plus B. And A times B is a class of a product, A times B. So one cannot simply make this definition because of the following reason. So if you define A plus B to be the class of A plus B, what might happen is that if you take another representative of this class or this class, you will get, for instance, element A plus P or something like that, add them up, and you can get a representative of a different class. So actually it's a little proposition that it never happens. So these operations are well defined. And this is a little exercise. But what is good about it, if we return back to our arithmetic module 7 example, so remember we had there problems like 3 times 5. So now we can simply say that the product is a class of a product, so a class of 15. And if we want, we can leave it like that, or actually simplify it, because 15 is in the same class of equivalence as 15 minus 5. It's the same as 8, which is the same as 1. And so on and so forth. Of course, it remains to prove that with this definition, Fp is actually a field. Okay, so now I want to make a few more general remarks about fields and things related to them. 2 remarks. Remark number 1. Over any field, one can solve a system of linear equations. So if you think about it, the definition of a field involves addition, multiplication, ability to divide, subtract, and so on. It's exactly everything we do when we solve systems of linear equations. And so, for instance, if you have a system of linear equations 1 times x plus 3 times y equal to 2 and x minus y equal to 3 in F5, one can solve it in exactly the usual manner. For instance, subtract and get 4 times y equals the class of minus 1, because again, when we subtract, we just subtract these two numbers, and this class is the same as the class of 6, if this is easier maybe. And then we are trying to solve this linear equation, 4 times y equal to 6 modulo 5. So, sorry, it's not 6, it's 4. And then we are trying to find such y, and such y is just 1, of course. So we have found y, and then x is, of course, just a class of 4. So in this way, we can simply solve systems of linear equations in any field. Complex numbers, finite field, and so on. So since I said already that linear algebra, in the most pedestrian terms, is about solving systems of linear equations, it's not surprising we first talk about fields. It's exactly the most general setting where we can talk about such things. Okay, so this is one thing. So another thing is that we will encounter another very interesting structure, which is called a ring. So a ring, R, is a set R and two operations absolutely similar, called addition and multiplication, such that properties 1a up to 1d, so all properties of addition are exactly the same. Hold. Then 2a, let me just remind you, is a times bc equals a times bc holds. Multiplication is associative. 2b also holds, there exists a unit. A times 1 equals to a. 2c is that, yeah, and that's it. And finally, property 3, a plus b times c is again ac plus bc. But also notice I have not mentioned commutativity. So ab is not necessarily ba. So if c times a plus b should also equal to ca plus cb. So now there are two properties here. So this thing is called a ring, and we'll see later a ring of matrices and many other rings. So if, in addition, for every elements a, b in R, a times b equals to b times a, R is called commutative. And if, in addition, for every element a inside R such that a is not equal to 0, there exists an element a inverse inside R such that a times a inverse equal to 1, then R is called a field. Thank you very much. I will see you later.